So we are discussing about Boolean loss simplification, right? We have discussed three methods to reduce Boolean loss, right? One is using Boolean loss, Boolean expression, to reduce Boolean expression. One is using Boolean loss. Second one is using K-map, and third one is using Queen-McCluskey or tabulation method, right? So we have discussed why do we need to reduce the Boolean expression. Why do we need to reduce the Boolean expression? To reduce the gates. Why do I want to reduce the gates? So, to simplify the circuit. What is the advantage of simplifying a circuit? Time consumption, less complexity. We have different reasons, okay, to reduce the circuit. So in today's class, we are going to discuss how the power consumption is going to reduce when I reduce the number of gates, right? Power consumption, because as electrical engineers, we should be much concerned about power consumption always, right? Energy consumption is a major energy. Demand is a major issue, and so in all the circuits, as much as possible, we are supposed to reduce the power consumed, right? So we are going to see how the power consumption can be reduced. See, this is a expression. So as already we know, we can when we draw a circuit for this, three inputs A, B, and C is the three inputs. So A and B is being given. I am drawing the circuit for this equation. Let this be equation 1. For this equation, I am drawing in. So equation 1. For equation 1, the circuit. So A and B is given to, what is this gate? What is this gate? OR gate, right? So to this OR gate, and then see another A and C. So this is C. Already we have A here. So A, I am giving A, and then C, right, which is being given to an OR gate. Then these two. So output at this point will be A plus B. At this point will be A plus C. And now these two are being given to what is this gate? AND gate, right? So it is given. So finally we will be getting the expression. So altogether, how many gates are here? 3 gates are here, right? See, every gate, when it is moving from 0 to 1 or from 1 to 0, right, a transition is there. Isn't it? A transition is there. That is, the transistor is switching from 1 to 0 or from 0 to 1, right? In both these things, in both these transitions, we call it a switching activity. So what is the switching transition or switching activity? Can anyone answer?
Switching activity refers to a number of times and a logical change is output state during circuit operation.
Okay. So what is the impact of switching?
Each transmission consumes the energy because it involves both charging and discharging, and the parasitic capacitance decay output.
Yes. So see, as already in a video I showed that every gate has transistors, right? So inside the transistors will be having parasitic capacitance, and this what is happening when a transition from 0 and 1 is taking place? The capacitance is charging and discharging, right? When the transistor is in one state, the capacitance is charging. When it is in 0 state, the capacitance is discharging, right? Am I right? So every time the capacitance is charging and discharging. So for charging and discharging, it obviously will consume energy, right? So power consumption will be there. So this is first equation, that is without any simplification we have drawn it, and so this is 3 gates are required. See, we have applied certain laws and we have reduced the expression, and finally this is the reduced expression. Let me consider it as equation 2. So I am drawing the expression for equation 2. If I draw the expression for equation 2, we have B and C, which is being given to an AND gate. Then the output B and C is given as input to or gate with A as another input. So B, C, and here A comes. So finally we will be getting the expression. So the same expression after simplification we have implemented or we have incorporated. So how many gates are required here? 2 gates. So obviously the gates are reduced, right? So as we have discussed in case 1, see in this first case without simplification it requires 3 gates, and with simplification it has, after simplification it has only 2 gates, right? See every time when it is executing this task, see suppose if I ask you to verify, whether this is equal to this, we have reduced it, right? And we are claiming that this is equal to this. Am I right? Right? If I ask you to verify, how will you verify? Right? You will be drawing a truth table. How many variables are here? 3 variables. A, B and C, 3 variables are here. So next column will be A plus B into A plus C, and then next column will be the second expression, A plus BC. If you have 3 variables, how many possible combinations will be there? How many possible combinations will be there? 2 power 3 combinations. So altogether 7 will be there. Okay, 7 possible combinations will be there, right? So see, you substitute 8, 0 to 7, right? 0 to 7. So, just substitute the values and find this. Find this value and this value. If these 2 values are same, then we can claim that equation 1, the thing what I have reduced, is right, right? It's going to be right, you can check it. Now see, when I am checking this, what is happening? The inputs or the variables is transitioning, or these gates is transitioning between zeros and ones. Right? See, you substitute from 0 to 7. Right? And check for executing this, how many transitions are required? How many transitions is done by every single transistor? Right? So see, obviously, when the number of transistors reduces, the switching activity also will reduce. Right? When the switching activity reduces, then the power consumed or the power dissipation also will reduce. Am I right? Yes, power dissipation also will reduce. Altogether, the power consumption will be reduced. So, when the number of gates decreases, the power consumption will be reduced. We can see this with the help of, see, 2 types of power dissipations are there. One is static power dissipation, another one is dynamic power dissipation. Okay. So, what is static power dissipation? Even when your gate is idle, when your transistors are idle, it is not doing any switching activity, static power dissipation, right? I am speaking about static power dissipation when your transistors, that is your gates, are idle. What is that inside the gates? Transistors, right? Once when your gates are idle, that is, it is not doing any switching activity. Even at that time, some power dissipation will be there due to the leakage current. Right? In transistor, you have learned MOSFET, right? See, always leakage current will be there from VDD to ground in a transistor when you see. Right? So, maybe due to improper insulation or maybe some other reasons, right? Some leakage current will be there. So, even there is no switching activities, leakage current will be there, and so power will be consumed because of that, and that is known as static power consumption. Right? And the static power consumption, what is the formula for power? P into I, right? So the static power consumed will be the supply voltage into the leakage current here, right? Because here the current involved is leakage current, right? So see, when the number of when the number of ICs increase or the gates increase, obviously this also will be having its own leakage current, this will be having its leakage current, this will be having its leakage current, right? So all the leakage current will be added up here, right? So when the number of gates reduce, the leakage current obviously will reduce. Am I right? Right? So see, this is if this is for one gate, then we will be adding up for all the gates. Okay. Now coming to, other than this, when switching activity takes place or a transition is there, we'll be having power, right? That power is known as dynamic power. Dynamic power. Okay, that what is meant by dynamic? Movement, changing, right? Dynamic is changing. That is when there is a switching activity or a transition, then obviously we'll be having dynamic power. So, the formula for that is of C V square. Here V is VDD. F into N. N refers to the number of transitions. F is the frequency and VDD is the supply voltage and this is the capacitance, right, in the transistor. So half C V square F into N. See here N refers to the number of switching activity, right? See, which is directly proportional to dynamic power. Okay, directly proportional to dynamic power. So when the number of switching activity reduces, the power consumption will reduce because that is directly proportional, right? It will reduce. So see, the switching activity will reduce if the number of gates reduces. Okay, so see, we have considered a Boolean expression and with two cases. That is one case without reduction and second case with reduction we have used. And see, go and check how many transitions is being done by this gate for executing, for verifying this expression. Okay, so every time it has to change from 0 and see first time A, B, C will be 0, 0, 0. Right? In the second case, A and B will be 0, C will be 1. So obviously here a transition will be there. Right? Every time this will be transforming. See, you can see this with mobile phones too. See, when you are playing some games, check what is the power consumption. Right? Based on the card, see, these are the factors which affects power consumption of any digital circuit, of any IC. Okay, because it is built up of transistors, right? It is built up of gates. So whenever gates is there, we will be having, whenever transistors is there, we will be having the switching activity, and this is directly proportional with power dissipation. And so, see, static power as well as dynamic power affects the performance of any digital circuit, right? So since as electrical engineers we are much concerned about the power consumption, and so always we prefer these kind of simplified circuits rather than this enlarged circuit. That is why we use either Boolean laws or K-map or P-McCluskey method to reduce a Boolean expression. Okay? Okay, thank you.